And we're going to do this example. I'm going to sketch a graph. Sketch a graph of the function f of x is equal to x cubed over 3 minus 400x. Okay, so I'm going to go through the checklist to find all the relevant features of this. First step, the domain. Well, f is a polynomial and it has a domain of all real numbers. So that step was pretty simple. That was part A. Next, let's find where are the x and y intercepts. The intercepts occur on the x and the y axis. So the y-intercepts occur when x is equal to 0. That's the easiest one to find. F of 0 is equal to 0 cubed over 3 minus 400 times 0, which happens to be equal to 0. So this gives me a y-intercept of 0, which tells me an xy pair. That pair is 0, 0. Okay, let's find the x-intercepts. X-intercepts. These occur where y is equal to 0, or where f of x is equal to 0, if you prefer to write it that way. F of x and y mean the same thing in this case. So I'm going to take the function f of x, which is x cubed over 3 minus 400x, and I'm going to set it equal to 0 and solve. First thing I want to do is, there's an x in both terms, so I'm going to factor that out. I get x squared over 3 minus 400 is equal to 0. I can set each factor equal to 0 and solve. So x times x squared over 3 minus 400 is equal to 0. First factor is x. I'm going to set that equal to 0. So that gives me one y-intercept. Next factor is x squared over 3 minus 400 is equal to 0. I only have one term that involves x, so I'm going to isolate that term. Add 400 to both sides, and I get that x squared over 3 is equal to 400. Multiply both sides by 3. I get that x squared is equal to 400 times 3, which is 1200. Finally, to solve for x, I'm going to take the square root of both sides, and I get that x is equal to square root of 1200, which is 20 times the square root of 3. Or if I put that into my calculator, I can get the decimal approximation, which is about 34.6. I also know that whenever I take the square root of both sides of the equation, I get two solutions, a positive and a negative solution. So I'm going to involve both of those here because the domain includes both positive and negative numbers. So that gives me 2 more points. Negative 20 square root of 3, 0, because I'm remembering that the y value is 0 on the x-axis. And I have the point 20 square root of 3, 0. Okay, so I have 3 pairs, coordinate pairs. At x equals 0, that gives me the point 0, 0. We already discovered that, so that's really not an extra pair. These are x-intercepts and then a y-intercepts occur at 0, 0. That also happens to be an x-intercept. Okay, so we have intercepts. Let's move on to the next step. Let's see if symmetry will help us out any. If you remember, if a graph is symmetric about the y-axis, i.e. if it is an even graph, if I evaluate the function f at negative x, then I get the function itself, f of x. If the graph is symmetric about the origin, i.e. if it is an odd function, then if I evaluate the function f at negative x, I get negative f of x, the opposite of the function. It looks to me as if both of them will require me to evaluate the function f at negative x. So maybe I start with that. F, go ahead and write what we're doing. This is symmetry. F of negative x is equal to negative x cubed, I'm still using my original function, over 3 minus 400 times the negative x. Going to simplify that. Negative x cubed is equal to negative x cubed. So this top one, what's the difference between these? This top one, I'm multiplying a negative x by itself 3 times. This bottom one, I'm multiplying x by itself 3 times, and the result is negative. Because if I multiply a negative number by itself 3 times, I get a negative number. So negative x cubed divided by 3 minus 400 times negative x becomes plus 400x. And I might observe that if I factor out a negative, and I get negative x cubed over 3 minus 400x. Well, this part here happens to be f of x. So it looks like to me f of negative x is equal to negative f of x, which fulfills the second criteria for symmetry, not the first one. So it appears to me that the graph is symmetric about the origin. Symmetric about the origin. So that's the point 0, 0. And what exactly does this mean? This means that if I have a point A, B on the graph of the function f, then the point negative A, negative B is also on the graph of the function f. So if I know one point, I know a second point as well. Okay. Okay, so I know symmetry, I know domain, and I know intercepts. Let's find out if this graph has any asymptotes. Asymptotes. All right, so we use algebraic methods to find asymptotes before. We're going to use calculus methods as we've done in our course. So horizontal asymptotes. I'm going to figure out, well, what is the limit as x approaches infinity of f of x? Well, I know what f of x is. I can go ahead and write that in. Limit as x approaches infinity of 1/3 x cubed minus 400x. This is a polynomial. I know from our discussion of infinite limits that this behaves like the leading term So this is equal to the limit as x approaches infinity of 1/3 x cubed. The degree is odd, and the leading coefficient is positive. That means this is equal to positive infinity. So there is no horizontal asymptote from this. No horizontal asymptote, at least as x approaches infinity to the right. I should check the other side. The limit as x approaches infinity of 1/3 x cubed minus 400x, oops, that should be negative infinity, is again, this is a polynomial, so it behaves like the leading term as x approaches positive and negative infinity. So it behaves like the limit as x approaches negative infinity of 1/3 x cubed, which this is an odd function. Leading coefficient is positive, so this is equal to negative infinity. That shows that there is also no horizontal asymptote as x approaches negative infinity. No horizontal asymptote here. So there are no horizontal asymptotes. How about vertical? Vertical asymptotes. Well, I'm going to lean on the domain for vertical asymptotes. F of x is equal to 1/3 x cubed minus 400x. And I am looking for values for which there would be division by 0, or perhaps that would cause me to take the square root or an even root of a negative number, or that caused me to have to input a negative number or 0 into a logarithm. Well, there are no such values. So I could also say that there are no vertical asymptotes. No vertical asymptotes. This function is defined and continuous for all x. Something that we could say in general here is, again, f is a polynomial. Polynomials never have horizontal or vertical asymptotes. Note that polynomials never display asymptotes. Asymptotes of any type. So we can just settle that here. Okay, that is all that I can do without finding the derivative. The next 3 or 4 steps all involve f prime or f prime prime. So let's go ahead and find the derivatives. I remember that f of x is equal to x cubed over 3 minus 400x. I'm going to find the first derivative. F prime of x is equal to derivative of x cubed, which is 3x squared times 1/3. Because another way that I can write this is 1/3 x cubed minus 400x. An equivalent way of expressing that. Okay, minus 400 times the derivative of x, which is 1, which is equal to 1/3 times 3 is 1 times x squared minus 400. So I have my first derivative. Second derivative, f prime prime of x, I can get by finding the derivative of this function, f prime. That is equal to the derivative of x squared, which is 2x, minus the derivative of 400, which is 0. So that's equal to 2x. F prime prime of x is equal to that. So I have my second derivative here, and I have my first derivative here. So I am set up to do all of the checklist items that involve those derivatives. Okay, so let's do part E. E is finding intervals over which this function is increasing or decreasing. Intervals of increase or decrease. Okay. And I'm actually going to do part G with this. I'm going to find any concavity or on any points of inflection and find where the graph is concave up or concave down. Concavity and points of inflection. Points of inflection. Part E uses F prime. Part G uses prime prime. But they're very similar in nature, so I'm going to do them at the same time. So, part E. I want to find intervals over which the graph is increasing or decreasing. The increasing or decreasing nature of a graph can only change where that first derivative is equal to 0 or the first derivative does not exist. Excuse me. Okay, so I'm going to take that first derivative. It is x squared minus 400, and I'm going to set it equal to 0. I'm going to solve that. Add 400 to both sides, and I get that x squared is equal to 400. Take the square root of both sides. I get that x is equal to square root of 400 is 20. Anytime I take the square root of both sides, I get a positive and a negative number. So I have two critical numbers there. Places where the derivative does not exist, where f prime of x does not exist. Well, again, f is a polynomial, or f prime is a polynomial, I should say. This is f prime, or this if you prefer. It exists everywhere. So there are no critical points for this particular option for finding critical points. I only have two critical numbers. Okay, while I'm at it, I'm going to find possible inflection points. So G, possible inflection points. Inflection points. These occur when that second derivative is equal to 0 or second derivative does not exist. Same process as I did before. I'm going to remember that the second derivative is equal to 2x, and I'm going to first of all set it equal to 0. The places where the second derivative is equal to 0. This is where 2x is equal to 0. If I divide both sides by 2, I get that x is equal to 0 is a possible inflection point. Second, places where that second derivative does not exist. Well, again, this is a polynomial. F prime prime is a polynomial. There are no locations where it does not exist, so I don't get any critical points from that, or any possible inflection points, I should say. Okay, So I have critical points, critical numbers, and I have one possible inflection point. Let's put all that on a number line, or perhaps 2 number lines. This is my number line for f prime. So I'm going to put the critical numbers on there. This divides the x-axis up into 3 intervals: negative infinity to negative 20, negative 20 to 20, and 20 to infinity. Going to use second interval, or second number line, I should say, for the graph of f, putting only that possible inflection point on there. And I'm just going to show where they connect. Okay. So this top one, I'm going to figure out, well, what's the sign of f prime? This bottom one, I'm going to figure out what's the sign of f prime prime. Okay. So I'm going to go ahead and let's see. What kind of test could I do? I'm going to test the sign of f prime in this interval. Say maybe I'll choose negative 30. Going to test the sign of f prime in this interval from negative 20 to 20. Say maybe I'll choose 0. And I'm going to test the sign of f prime in the interval from 20 to infinity by maybe choosing 30. F prime of negative 30 is equal to negative 30 squared minus 400, which is equal to 500, which is most certainly positive. So that first derivative is positive here. F prime of 0 is equal to 0 squared minus 400, which is equal to negative 400. All that I really care about is the sign. That first derivative is negative here. And then finally, f prime of 30 is equal to 30 squared minus 400, which is equal to positive 500. All that I care about is the sign. So the derivative, first derivative, is positive in that interval. Okay. Now I want to figure out, well, is the graph, I have 2 intervals that I've split the x-axis up into when it comes to concavity, negative infinity to 0 and 0 to infinity. Let's figure out, is the graph positive or negative in those intervals, or is the second derivative, I should say, positive or negative? So I'm going to test values. Test maybe negative 20. Maybe I'll put the critical number in there. Maybe I'll test 20 in this interval. Okay. So f prime prime of negative 20 is equal to 2 times a negative 20, which is a negative 40. I really care about it being positive or negative. That's about it. It is negative in this interval, so that means the graph is concave down there. And then similarly, f prime prime of positive 20 is equal to 2 times 20, which is equal to positive 40. Okay, I really care about it being positive, and that's about it. So that means the graph is concave up in this interval. Back to my first derivative. If the first derivative is positive, the graph is going up in that interval. First derivative is negative, the graph is going down in that interval. First derivative is positive, means the graph is going up in that interval. So this is essentially E. and this is g. All right, what could I say now? What are my conclusions? I could probably say that in this interval, from negative infinity to negative 20, the graph's going up from left to right, which means it is increasing in that interval. And similarly, it is increasing from 20 to infinity. Okay. The first derivative is negative in this interval from negative 20 to 20. So that means the graph is decreasing in that interval. Okay. As for part G, for concavity, instead of the graph is concave down in this entire interval from negative infinity to 0, and it is concave up in this entire interval from 0 to infinity, because 0 is the only location where the graph can change concavity. Okay, so let's see here. I have a nice little diagram that helps me to answer the remainder of G and to answer F. So while we're at G, let's go ahead and finish that up. Are there any inflection points? Inflection points. Well, inflection points are where the sign of the second derivative changes, or where the graph changes concavity. It does appear that here is the location where the graph changes from being concave down to concave up. It can only make a change where the second derivative is equal to 0, and that only occurs here. And I know it has to change from being concave down to concave up at some point, so it must be here. So this must be an inflection point. An inflection point. I actually know the y value where x is 0. We discovered it before. So the inflection point is 0, 0. Also happens to be the x and the y intercept. Okay, that was the remainder of G. Let's go to F. F is where I want to classify the maximum and the minimum values. Well, I have a nice little diagram that allows me to use either the first derivative test or the second derivative test to discover the answers. By the first derivative test, then I might observe that this is a critical point, critical number, negative 20. To the left of that critical number, the graph is increasing. In other words, the first derivative is positive. And to the right of that graph, the first derivative is negative and the graph is decreasing. So this is the location of a relative maximum. This is the location of a relative maximum. And then similarly, this critical number has a first derivative that is negative to the left and positive to the right. So the graph is decreasing to the left and increasing to the right. That means by the second derivative, or by the first derivative test, this other critical number is the location of a relative minimum. So by the first derivative test, negative 20 is the location of a relative max, and 20 is the location of a relative minimum. By the second derivative test, well, earlier I tested actually those critical numbers in the second derivative. and we discovered that the second derivative at that first critical point, -20, is less than 0. And by the second derivative test, this tells me that -20 is the location of a relative maximum. The exact same thing that I found here. And very similarly, the second derivative at x equals +20 we found is positive. So that tells me that 20 is the location of a relative minimum by the second derivative test. Right here. So I can tell by first derivative test or second derivative test that -20 is the location of a relative max, 20 is the location of a relative min. If I'm going to graph this, perhaps it would be a good idea to actually find the y values corresponding to those max and min points. Okay. So f of -20, this is the y value, i.e. the maximum value or relative max value for the function. It's equal to -20 cubed over 3 minus 400. If I put that in my calculator, I get 5,333 1/3. So something very large. That gives me a point. That point is -20, 5,333 1/3. And then very similarly, f of 20 also happens to be equal to 5,333 1/3, except it is negative, as we could expect, because this is the y value for the minimum location. This gives me the point 20, 5,333 1/3, except the y value is negative. Okay. So I have a couple more xy pairs that I can put on my graph. So it looks like we have successfully explored all points on the checklist. Last thing to do is I want to use that to make a sketch of the graph. It looks to me as if the scale on my y-axis has to be pretty large because my relative max and min go up and down quite a bit. Go up pretty high and down pretty high. So maybe I will scale the y-axis by thousands. So this is 1,000, 2,000, 3,000, 4,000, 5,000, 6,000. This is -1,000, -2,000, -3,000, -4,000, -5,000, -6,000. My critical numbers are at -20 and +20, so they're not quite as large. Perhaps I'll make my x-axis go up by tens. I have a x-intercept at about 35, so it has to go to at least 40. And similarly to the left, this is -10, -20, -30, and -40. And the axis will keep going. Okay, so now maybe let's start by putting those xy pairs that I know are on the graph onto the coordinate plane. I know that there are intercepts, x-intercepts at -34.60. It's one of my x-intercepts, and at +34.60. I know that there's an x-intercept and a y-intercept. They're happen to be the same at 0, 0. So those are my intercepts. I know that there is a relative maximum occurring at negative 20, and it has a y value of 5,333 1/3. So maybe right there, that might be a little too high. Let me put that down a little tiny bit. Maybe right there. A little more like it. And then similarly at 20, negative 5,333 1/3, this graph attains a relative minimum. Oops. So it's about right. That's more like it. Okay. So I have those key points on there. What else do I know? Let's see. I know that the graph is concave. Well, let's start with increasing, decreasing possibly. I know that from negative infinity to negative 20, the graph is increasing. I know from negative 20 to positive 20, the graph is decreasing. And I know from 20 all the way to infinity, the graph is increasing from what we said before. I know from 0 to, or from 0 to infinity, the graph is concave up. I know from negative infinity to 0, the graph is concave down in that entire interval. Okay. So that means it's concave down here. It's concave up here. Okay, I could probably connect the dots. I know that this graph is continuous and its domain is all real numbers. I know it's increasing, so it's going up from left to right here. It goes through that point. It keeps increasing, going up from left to right until it hits this point. And I know that's the location where it turns and it starts decreasing. It is decreasing, it's concave down. Concave down here. And then it does not start being concave down until this point here. This is an inflection point. So at that point, it turns and starts being concave up. It's decreasing until it hits this point, which is a relative minimum. This is a relative max. And then at that relative minimum, it turns around and it starts going up from left to right. I know that it crosses the x-axis at this point, the x-intercept, and it keeps going up forever. Keeps going up and keeps being concave up forever.